All right, so that was exponential growth. Next one we're going to talk about is logistic growth. Now, logistic growth, remember, if we see the shape of that graph, it was this S-shaped. There was a carrying capacity that curve was reaching. So I'm just going to sketch it out real quick, just as a quick reminder. So it looked something like this. And then there was this carrying capacity that the line was going up to. Again, this is the perfect mathematical world. We learned in biology that it might go above it and below it and above it, etc. Now, in our mathematical model, we have to take this into account, right? We have a carrying capacity. That's going to affect how quickly our population is growing. So you'll notice some similarities. First off, we have dn over dt, the change in the population over time. Again, typically time is just a generation. And then we have r times n. So here's our exponential growth. We have the growth rate times the number of individuals. But you see there's a new term here, this k minus n over k, where k is the carrying capacity. It's whatever that top value is that we are trying to reach. So we have k minus n. This is the same exact n. How many individuals do you have divided by k? And before we talk more about our problem and whatnot, let's talk about this term, this k minus n over k. The question is what happens as n? What happens as the number of individuals in our population approaches k? So let's use an example where k equals 100 and n equals, let's go 10. And let's just solve that term. So we're saying, hey, we have a carrying capacity of 100 individuals, but right now we only have 10 individuals. We're actually pretty low compared to the carrying capacity. So if I solve for this term, we have 100, which is, again, k minus n. So 100 minus 10 divided by k, which is 100. So this is 90 over 100, which equals 0.9. So when n is pretty far away from k, when the number of individuals is pretty far from that carrying capacity, that term, which is going to be between 0 and 1, is closer to 1. Meaning that when I do r times n, I'm going to multiply it by this term, in this case is 0.9. It's going to be a pretty high value. R times n is going to be pretty much r times n. I don't have to modify it too much. I mean, I'm multiplying it by 0.9. Sure, it's going to make r times n a little bit smaller, but 0.9 is pretty close to 1. Now, let's say that our carrying capacity and the number of individuals are close together. That, let's say I have, again, k equals 100, n equals 90. So the number of individuals is actually, it's approaching that carrying capacity. It's getting there. That might be, looking at our graph, that might be here. Whereas when we had 10 individuals, that was down here. So here we are at this 90. We're getting close to that carrying capacity, meaning we can't add tons and tons of individuals. Only a couple more individuals can be added. So again, if we look at that term, 100 minus 90 over 100, which equals 10 over 100, which equals 0.1, which means my r times n, whatever that number is, I am now multiplying it by 0.1. I'm essentially taking a tenth of that number. I can't add r times n. That's going to be way too many individuals. We're getting so close to the carrying capacity. So this term, this carrying capacity term, is getting closer to 0, meaning that the number of individuals being added is going to be pretty small as we reach that carrying capacity. So this bullet point of what happens as n approaches k, this is just saying, hey, when n is pretty close to k, how does the population change? Well, we're not adding a lot of individuals. Well, what if n is really far from k? Well, then we're probably going to add a lot more individuals. Okay, I just wanted to explain that just because it kind of helps to visualize what's actually happening in this equation. So down here I have a word problem. It is actually the same exact word problem. I've got 100 diatoms, but now I'm experiencing logistic growth. 45 out of 50 diatoms are produced, and 1 out of 40 diatoms die. And same question, how many diatoms are there at the start of the 5th generation if my carrying capacity is 500? So I've now introduced that K term. As a reminder, so R is going to be the same. We have 0.9 as the birth rate. We have 0.25 as the death rate. So that means our R equals 0.875. This is the same exact thing as last problem. You can resolve it the same exact way. All right, so here we have a new table, and this new table is for logistic growth. Again, I have added more columns than you actually need, but that's so that I can show every single step. As you get more comfortable with this, you can delete some of these columns and kind of combine some of these steps together. I have the reminder up at the top of what the logistic growth equation is. Remember, our problem starts out the same way, where our n is 100. And then what each of these columns are different parts of the equation. R times n has its own column. K minus n over k has its own column. dn over dt has its own column. Nu n has its own column. Again, you don't need all these. I'm putting them here on purpose. So like before, I'm going to go through the first 2 rows together. Then you'll pause this video and then come back to view those answers. So our R, as a recap, is 0.875. So R times n is going to be 0.875 times our n, which is 100, and this is going to equal 87.5. We saw this with exponential growth. This is actually the very first and same thing as exponential growth. But we have a carrying capacity. We have a carrying capacity of 500. So let's see what that term shows us. So we have 500 minus our n, which is 100, divided by 500. This is going to equal 400 divided by 500, which equals 0.8. So 0.8, it's close to 1, meaning that we're still going to add quite a few individuals. We're not shrinking yet. We're not so close to the carrying capacity yet. And so if we do dn dt, remember dn dt, looking up here, is r times n times k minus n over k. Essentially, I want to take this term and multiply them together. And so I'm going to go ahead and do that. That's 87.5 times 0.8, which equals 70. So this dn dt is saying 70 individuals. My population changed over this time period or generation by 70 individuals. This is a positive number, meaning that I am increasing my n. So our original n is 100. We have now added 70 individuals, so my new n is 170. 100 plus 70. All right, let's carry this down to generation 2. So here we have 170 individuals. We're going to do r times n, 0.875 times 170, our new population. And this equals 148.8. Here is where a lot of students mess up, and I'm going to put a little star next to it. A lot of students mess up when calculating this when calculating this k minus n over k term. So k doesn't change, right? Our carrying capacity is still 500. Minus n. Our n is no longer 100, right? We are in a new generation. Our new n is 170. So make sure every generation you are updating this. This does not stay 0.8, right? As our population is growing, we are getting closer to our carrying capacity. So it's 500 minus 170 over 500, and this equals 0.66. You see, this number is lower than before. That's what we expected. We're getting closer to our carrying capacity, meaning we're going to be adding less individuals. dn over dt, so we're going to multiply these two together, so that's 148.8 0.8 times 0.66, which equals 98.2. So our population has changed by 98.2. So I had 170, we are adding 98.2, and this equals 268.2. We ended with 268.2, so the next generation, we are going to start with 268.2. So on and so forth. So go ahead, pause here, and finish filling in this table. All right, so here is your answers for all of these. Again, if your numbers are a little off, that's fine. If you're off by 10, even for some of these larger numbers, maybe 20, you're probably fine. It's probably just rounding. If it's closer to 20 off, there might be an issue. So try to figure out where which number might be the most different and where does that start, because maybe it was just a simple calculator problem. And you'll notice that I only have like one decimal place for the big numbers, and then for this k minus n over k, what I do, and I know I told you we wouldn't use significant figures, but I do 2 sig figs, so this would be a 0. So I have 2 decimal places, 2, 2. Remember, with significant figures, leading zeros aren't significant figures, so I have 2 numbers here. So that is what I personally do. It's helpful, especially for the k minus n over k, because these are decimals, right? If you have decimals, you need more decimal places. When you have big numbers, you don't need decimal places. Anyway, again, if you're between 5 to 10 off, you're probably fine. It's probably just rounding. Again, I put mine in Excel, which is using all the decimal places, whereas you were probably rounding for each step, which is totally okay. When I make a key in the future, I'm probably just going to make it by hand and do the rounding and probably end up with the same exact values as you. So the last thing that I want you guys to do is, we had more or less the same population growth rate, same starting population. It's just one of them had a carrying capacity and the other one didn't. And so the graph that you made of your exponential graph earlier, what I'd like you to do is, using that same piece of graph paper that has your exponential growth curve already on it, use that same exact paper to draw a second line. Draw the logistic growth line. Draw this population. You already have the same generations. Your first data point, generation 1 with 100 individuals, is the same. But you're going to notice generations 2 through 5 are different. And you can very easily compare, even though you have more or less the same population, how logistic growth really changes that growth within this population. So that's where we're going to stop. The lab goes into this a lot more, and you can use tools like Excel to figure this out instantly versus going line by line by line. But I think it's important knowing line by line by line so that you really understand where these numbers are coming from, and then you also understand if something just doesn't make sense. Alright, so good luck with this, practice this, but again, you're using basic algebra. If you're using anything other than addition, subtraction, multiplication, or division, you're doing something wrong. Alright, good luck.